Hi, this is Roger from Kankan Labs, and today it's the third part of our series about our EMI DC filter, which in the end will look similar to this one, only much more sophisticated. We're just getting or have ordered the PCBs from China, and in around 2 weeks we will have our improved prototype ready. But there may be some questions left open to one or the other of you from the first part. And that's why I just explained still 2 or 3 points that you might have asked yourself. First of all, let's start. Why is it sufficient to suppress 100 or 120 Hertz instead of the 50 or 60 Hertz line frequency? A few watchers have asked this question, and for that let's go back to this picture of a typical switch mode power supply. And this here is the mains input, and here you already can see there is a full bridge rectifier and to charge the charging capacitor. And now let's take a look. Of course, we all know that the line frequency, this is of course a, depending on the region where you live, 50 or 60 Hertz frequency noise or hum in this case. But how does the waveform look like behind the bridge rectifier? And there it's this way. And if you do a Fourier analysis or a Fourier transform, you will see now that the fundamental frequency of a fully rectified mains frequency signal is the double frequency, because the lower half of the sine wave is flipped over, and we get a repetition of the signal with double the frequency, and that's the reason why we usually get 100 or 120 Hertz hum. So it's sufficient if we take care of this frequency, because usually the basic main frequency doesn't get through, and we just want to suppress the noise that comes from switch mode power supplies, and they usually all have a full bridge rectifier, and that's why we concentrate on the suppression of 100 or 120 Hertz hums. So you might remember that I've shown you the 4 sources of noise: the basic switching frequency of the switch mode power supply, which gets over to your, or which is superimposed on your DC voltage. Then we get so-called common mode interference, which we'll explain again just in a few minutes. We get what we just said, the 100 Hertz or 120 Hertz hum or noise that couples from the fully rectified primary side over a coupling capacitor to the secondary side, and there again superimposed on your DC voltage. And we have the earth coupling because we don't have an ideal earth where the different connections to earth from primary side to your load side, there is inductance in between and there is resistance in between. But in some switch mode power supply there is also a 5th source of noise, which is very annoying, and that comes from so-called discontinuously working switch mode power supply. Now, what is that, you may ask? And we just imagine that we have at the output of any switch mode power supply, we have a capacitor which gets, we don't want to explain how a switch mode power supply works, but you can imagine that your storage capacitor, let's call it that way, is charged up with little bits of charge. And when you put little bits of charge into a capacitor, the voltage will rise up. When we assume that in the beginning it has 0 voltage, then it will ramp up with every, or we should better show it this way, with every cycle of your switch mode power supply, the voltage ramps up a bit. And then finally, we of course have the desired output voltage. And there is some comparator with a threshold setting. And this is simply adjusted to stop charging the storage capacitor when the output voltage has risen above the threshold that is set for a comparator. So here we are just a little bit below the desired output voltage, and the next charge gives you a little bit above. Now, if we have only a light load, then of course from now on the voltage will, again due to discharging of the storage capacitor by the load, and now let's first of all presume a light load with a big resistance, then it will slowly start to decrease up to a point where it's slightly below the threshold voltage. Of course, the comparator which switches the switch mode power supply at this point off and then here on again has a little bit of hysteresis, just not to oscillate. So here the point is reached where the comparator will switch the switch mode power supply again on until it gives one or more charges until it's again above the threshold voltage, and this repeat with a constant load. This gives you a constant noise frequency which can be in the kilohertz range, which means the last bit of charge is enough for around 1 or more milliseconds until the voltage drops again below and the comparator again says, oh, now I'm below my desired output voltage, I have to switch on the switch mode power supply again, the oscillator of the switch mode power supply, and supply again some charges into the storage capacitor. So, and depending on the load, this can be only microseconds, but it also can be milliseconds. And if you have a constant load, then you will get a constant noise from this so-called discontinuous mode switch mode power supplies. I hope you understood the principle that this behavior simply comes from, at this point, the switch mode power supply or the oscillator or the output is switched off. That's why it's called discontinuous. It simply stops to put charge into the storage capacitor, and only when the voltage has dropped below the threshold voltage, minus the hysteresis, minus a few millivolts, then it again switches the output or the oscillator on again. And the time between switching off and switching on, that gives you usually a frequency in the audible range, and that's why it's so annoying. It can be much more annoying than the 100 Hertz or 120 Hertz hum, because if it's in the kilohertz range between, let's say, 500 Hertz and 4 kilohertz, that's when our ears are our ears are most sensitive, and so this is most disturbing, and it's just in a range where we can hear it. If it would be above 20 kilohertz, there would be no problem for us to hear it, but in radio reception circuits, this is a very annoying source of noise, but it's not always present, only with switch mode power supplies that are working in discontinuous mode. Sorry, I forgot an I. There are more modern ones that are working in semi or fully continuous mode, and this works in a way that, for example, only the oscillator frequency is changed when the output voltage is slightly above the threshold voltage, or that the output transistor, which charges first of all the inductivity, the centerpiece of any switch mode power supply, that simply the on time is changed, or it's the output transistor is not fully switched on. So there are different ways in modern switch mode power supply how you can suppress this switch on and switch off at this point, and here switch on again, but which gives you a more kind of analog regulation of the switch mode power supply. But more simple ones have exactly this behavior and give exactly this noise. So let's just sum up again the sources of noise in order of frequency. We have the 100 or 120 Hertz hum. We might have in the kilohertz range noise from discontinuously working switch mode power supplies. We have noise in the range 50 kilohertz to let's say 5 megahertz, that is the switching frequency. And we have the harmonics of the switching frequency, and the harmonics can go up to many dozens of megahertz. So this can go even into the FM range, and then we get all sources of noise by coupling of noise from the earth, which we call earth coupling, and this can have any frequency range. So that's why it's very difficult to construct a filter that can really filter out from 100 Hertz up to, in our case, we only need up to 30 megahertz, which is the end of the shortwave range, because the filters shall especially suppress noise for radio circuits. And this is not trivial to construct a filter which has such a large range. So that was it for the explanation of the fifth source of noise by discontinuously working switch mode power supply. And now let's go over to again explain, or to slightly more explain in detail what common mode noise is. So before we explain common mode noise, we again take a look at the opposite. That's differential mode noise. You can imagine this as, here we have our voltage source, which first of all is a DC source, and superimposed on this DC voltage, here we have the ground connection, superimposed on this is our noise. So now we have here our load, And of course we have a line going to the load and a line going back from the load to ground, because the current has to circulate, and if we have noise superimposed on the DC voltage, this noise will flow in the line to the load in this direction and from the load back to ground in this direction. So this is differential mode noise, and we'll see after the explanation of common mode noise how this is filtered out, what measures we can take to filter this out. But now let's go over to what is the difference to common mode noise. So let's again take a more detailed look at what common noise is caused by and what's the remedy to get rid of it. We'll draw again our voltage source, which again is first of all a DC power source, and we have the path or the connection to our load, and we already know that differential mode noise travels just as the DC current this way to the load and to the ground connection back in the other direction. And now we have seen that we also have the parasitic connection to Earth via some parasitic capacitance. And Earth is neither is it clean nor is it perfect. We already mentioned a few times we have parasitic inductance on the Earth line and ohmic resistance. And here on the Earth we have sources of noise that are simply coupled from other switchboard power supplies or anything else, and they generate a voltage here. So here we have a noise source from wherever, and this generates a voltage through this parasitic capacitor into our path from the DC voltage source to our load. And now comes the important thing. This noise source travels over both paths, over both lines in the same direction to our load, and from there again through parasitic capacitance to another point of our Earth connection. Now, depending on whether the noise source is greater here through this capacitor, then it travels on both paths this way. If it would be greater here, it would travel on both paths the other way around, but that makes no difference. The important thing is that common mode noise travels on both paths to the load and back to ground in the same direction. So now you perhaps can understand why what we do usually to filter out noise, a capacitor, doesn't work here, because now on both sides, on the upper and on the lower side of the capacitor, the noise source would have the same phase, and so there's no voltage difference generated by this common mode noise on the positive and negative side of the capacitor, so it has no action on the noise and cannot filter out the noise. And the same would be true for an inductor, which we also can use to filter out differential mode noise. Again, there is no effect. So what do we do now? How to filter out this common mode noise? Now, there is only one and only one electronic component that I know of that is able to filter out common mode, and that is called a common mode choke, or the German translation, or the translation of the German designation would be current-compensated choke. And it only takes you a few seconds to understand how it works. Sorry that this is a German diagram, but anyway, I'll explain to you all the words. Now, it is a toroidal choke with two windings, and let's see what these two windings make with differential mode noise and what they act on common mode noise. Now, the blue arrows designate the differential mode current. Remember, we have a DC current, and superimposed on it is first of all the differential mode noise, and the blue arrows designate as well the DC current and the superimposed differential mode noise. And now the current travels through the first coil and generates a magnetic field here clockwise, and it flows out of the toroidal coil again to the load and then back from the load. And now you can see it goes through the second winding on the same toroidal ferrite core, and the field generated by the backflowing current has the opposite direction. It goes counterclockwise, and if the two windings are exactly the same, then the two magnetic fields perfectly cancel out each other. So for the DC, this has two effects. The ferrite core doesn't get into saturation by this heavy DC current. It can be up to many amps. In our case, we designed two kinds of the filter, one which goes up to 2 amps, the other one can go up to 5 amps DC current, but the DC current does not generate any resulting magnetic field, because both fields in the current flowing to the load and back from the load to ground again, they cancel each other out. So the common mode choke has basically, first of all, no effect either on the DC current, nor, except of course for the ohmic resistance of the copper windings, it has no effect on the DC current and no effect on the differential mode noise. But what about the with the red arrows, with the common mode noise? Now the common mode noise flows here, as you can see by the direction of the arrows. It flows in this direction and generates also a clockwise current and magnetic field inside the toroidal core. But the other side has now the same direction as what we here have as the backflowing current. It doesn't flow back. It flows, as we know, in the same direction, but because of the winding direction, now it has also a clockwise magnetic field in the toroidal core, and now the full inductivity of the winding, or of the toroidal inductivity of the common mode choke, the full inductivity now works, and it suppresses the common mode noise, or the current or the voltage generated by the common mode choke. You can look upon it as if we have a very great resistance for the common mode noise because of the kind of the two windings, and we have nearly zero or only the copper resistance for the DC current and for the differential mode noise. So think about it for a few seconds, and it's really an ingenious component how to pass DC current and how to suppress differential mode currents generated by differential mode noise. So this is the one and only component you can use to get rid of common mode noise superimposed on a heavy or big DC current to filter this out. So on the right side of the common mode choke, there will be only a heavily suppressed common mode noise depending on the value of the inductivity of the common mode choke. And as in many cases, the bigger the better. The higher the value of the inductivity of your common mode choke is, the better it will suppress common mode noise. But of course there's a limit. The reason is, or the question is why? Well, when you want to get a high inductivity, you need many windings. Many windings mean more ohmic resistance, and so in the end you have to make a compromise between the size of your common mode choke and the maximum current that you have to transport, the maximum DC current, and then you select the highest inductivity you get that still accepts your max DC current.